You can also do something, you can also turn these two constraints off, and on the Python code, you can tell exactly when the cell is going to have a link and when you're going to destroy the link. So that's something that you actually need to make those convergent execution movements. The link that they create are not based on this criteria, but it's based on, I select those two cells and I check some criteria, and then I create the link between those cells. And then the criteria to break those links is the frequency at which the links are created and broken. So one thing that you can do, you can make all these maximum number of junctions to be 0. Okay. And when you do that, effectively no link is going to be created in your simulation. Okay. Nothing will happen. Because the maximum number of junctions that they can have is 0. But you can then activate this tag here called local, which allows to, from the Python file in the steppables, to manually make a link between two cells and manually delete this link between two cells. And then you can use the criteria that you want. Then you're happy? Okay. Yeah, so here's A, B, B, B. You also note that you also have these internal parameters, okay? And this is applied for the case where you have a cell that has other domains inside it. So for now, you have been dealing with the case where all your domains in the POTS modeling is just represents one cell, okay? But later on, you may have a situation. Later on, you may have a situation where, as James showed before, where you have a cell, and you have one domain that's the membrane, another domain is the cytosol, another domain that is the nucleus between the cells. So in this case, you have still 3 cell types. One type is membrane, the other type is the cytosol, and the other type is the nucleus. And you can have another cell nearby, which also has a membrane. Oops. Also have a cytosol and also have a nucleus, right? And you can make you can choose to make links between the nucleus and the cytosol. It does not make much sense in this case. Or if the nucleus and its cell membrane, so that would be internal parameters because are compartments that belong to the same cell. Or you can also have connection between the nucleus and the membrane of the neighboring cell, and then, or the cytoplasm of the neighboring cell. Again, this particular example here is very, doesn't make any sense. But these will be the parameters between, so the first 3 sets of parameters are between cells of different cluster domains. And these internal parameters are between compartments of the cell's internal domains. Does it make sense? We will cover cell compartments later. Maybe a better example is, let's say you want to model a epithelial monolayer, and the epithelial cells, they are arranged, well, they're an epithelium, so they have let's say a basal domain, an apical domain, which face the lumen, and the base domain face the ECM. And by default, they'll have some kind of domain or something that is in between those two, which is neither either lateral or neither basal or apical. Okay. One way to make cells to elongate is to add those kind of a length constraint between the basal and the apical side of the cells to make them a given height. Okay, so that in this case you'll be using an internal parameter between cell type basal and cell type apical, and that will make sure that it's elongated. Another thing that you may want to do is want to add a link or a link constraint between the neighboring two apical domains. You know that in real cells, they have this adhesion belt with junctions between neighboring cells, which is usually subapically or very near the apical side of the cell. So you can model this very tight junction between the cell neighbors in the epithelia as a kind of link between your modeled apical domains of the neighboring cells. So here you can also set another kind of link constraint between them, but this time you're going to be, it will not be an internal parameter, but it's going to be just a parameter between cell apical with the other cell apical that are not part of the internal compartment. Well, every cell has an ID, right? Which is unique. Okay, so this is going to ID 1. Now, well, all the cells, they have an ID, right? A unique ID, a unique identifier, your social security number. Okay. That's why cell and cell list that you're using in here is not a really good term. You should if I was the owner of CompCell, then I would have, instead of using cell, we'll use domain. So for domain in domain list, that's what I'll be using. Okay, and then domain you have types of domains, but each domain that you put is a single entity with a ID, domain ID. Okay, but on top of this ID, you can also add another number, which is called the cluster ID. And all the domains that have the same cluster ID so all this, so we have apical core and basal side, and they all have the same cluster ID. So that's how you know that they are part of the same cell, and that this base compartment belongs to this cell and not to this cell. Okay? So you're calling all your domain cells, because in most of the CompCell cases, a cell is defined by a single domain, a single kind of domain. But you may want to do more complex simulations where your cell is made up of multiple domains. Okay? So maybe a better term will be this the domain ID and this the cell ID. Okay. So when you create any kind of domain in CompCell, it has a unique ID, and it also has a unique cluster ID, which are usually the same number. But as I create those kind of structures like this, I reassign, okay, I first create this domain, and then I create this one, and then I reassign this cluster domain to be the same as this one. So I know that they're the same cell. Then I create this apical part, and then I reassign the cluster domain of this apical part to be the same as the cluster domain of this other two. Therefore, that's how I know that this is a single entity or a single cluster. I can see maybe in the future, you may have 3 numbers if you want to make something really complicated. Or maybe not, maybe just 2 ideas will be enough to describe most of the things you want, okay? Neighboring order. So did Maciek explain exactly how the energy contact works? Because you basically go with 4. You have your pixel, and then you have your neighboring pixels, right? And when you make your contact, you look over. This will be the first neighbors of your pixel. This will be the second neighbors of your pixel. So this is neighboring order 2. You also have the third order neighbors of your pixel. And you also have the fourth order neighbor of your pixels, which will be this. Okay, first order, second order is going to be square, third order, I square if those kind of cross, and a fourth order, this kind of stuff that is more and more resembling a circle, right? So this means that a cell here, so let's say this is a cell, this is the membrane. So this pixel of the cell can sense 1, 2. So if you have another cell that is here, it cannot feel it because you can go up to 1, 2 pixels this way, right? But if the neighboring cell is actually here, this other cell can already feel it by the contact energy because it has a range that goes up this far. So it can already see the pixel belonging to that cell. So here, if we say that your neighboring order is 4, this means that as soon as the neighboring cell gets 1 pixel away from the other one, they can already feel each other and you can already make a link between them. So you can make, so this can adjust to be bigger and bigger and bigger. So you can, even if you're very far away, you can still make the link. If you use 1, they have to actually be touching each other. Okay. If you use 2, this means that if this cell here can actually make a contact with this cell here, even they have a edge, yeah, they already can make a contact, a link, even they are not sharing any surface. Make sense? Yes. Yes, it's the same. You don't do distance kind of exponential decay, so anything like attenuation like that. If you say it's hard, it's on or off. You either count or do not count. Maybe a better implementation would be like this, but I'm not sure how much you gain from doing more fine like that. Yeah.
And the other question I have is that I don't really like center of mass.
Between the...
Yeah, because it depends on the shape. Right?
But it's the easy ways to implement this. Yeah, I know, because it's not... Yeah, because in this case, when you connect center of mass, I cannot extend the page. In reality, when you pull 2 cells that are linked together, that's kind of the shape they'll have. And in reality, the tight junction of the cells is really this junction, right? That's why they make this finger-like. But the way we implement it, if you just pull those cells together and not yet break the link, that's going to be the shape of the cells. Yet they will still be like linked, right? But if you do this kind of implementation, then the shape of the cell will be more realistic. So ideally what you have is kind of links that's not associated from the center of mass, but 2 points on the surface of the 2 cells that cannot be taken out. Something like this. That we, or if they have a link, they can never totally break their surface, something like that. So something that, some kind of global connectivity for those 2 cells that do not allow them to have a, they have to be continuous with one another. That will enforce this kind of shape. That will be a much better implementation. Yeah, I agree with you. More questions? Can we finally do the simulations? Yes. Okay, so you create your file, right? And then you put here. So out internal parameters. We are not doing complex cells, so just go ahead and comment them. So here, so we have these parameters, internal parameters. Let's just comment the internal parameters. And let's make, I forgot about this local. Comment back again. The local here at focal point plasticity. Comment, we are not there yet. Okay. And let's make all the number of junctions to be 0, except for, let me see here. Let me just look at, I don't see any, okay, cancel. Except for cell B and cell B. For cell B, let's make it 6, which is the average number of neighbors that you have in 2 dimensions with objects of the same size. Anisotropic shapes. Okay. So cell A and cell A, let's make 0. Cell A and cell B, let's make 0. And cell B and cell B, let's make 6. Target distance 7, which is usually equal to the diameter of the cell, so going to be equal to the distance between 2 cells on average. And maximum distance 20. Save this, and now let's play the simulation. So if you have all this, let me just try to get those 2 windows together. So I'm going to here in the player, file open simulation. I'm already in the simulation, sorry. So if I want this to go away. No. So stop play. Okay, you're maybe not seeing anything. Are you seeing anything? No, that's maybe because you're not actually visualizing. You have to go here to the menu, visualization, and click on FPP links. When you click that, then maybe you can see actually the links. Do you see? Now? You cannot select it. Maybe we don't have it. Are you playing the simulation? That
I'm running the simulation here. And this is my.
Okay. And
Should I stop it?
Stop it. Maybe you are still playing the version that you did not have the links. Yeah, you're playing the other one. Click. And you see, right? So right now the links, well, you can see that the yellow cells, or at least in my color scheme, move a little bit more than the green cells because the green cells are more constrained, right? The other thing that you can do, you can go here, click on the plugin focal point plasticity, open the last one, which is the B cells and B cells. And instead of having 7 in the target length between the cells, let's make it 4. And let's guess what will happen. What you guys think will happen? I'm changing the target length from 7 to 4. So all those links that you see here, right now they have a target length of 7, which is more or less the average distance between the cells. But now I want to shrink the target distance, right? So if I do this, let's play. Maybe it doesn't have that dramatic effect I was hoping for. But you can also always increase the lambda to be a little bit stronger. Okay, it didn't have an effect. Then make it 2. Okay, let me do something. Let me increase the temperature to 15 so to make the cells can move a little bit more. Did you guys play with the temperature? No? Okay. Okay, so let me explain what temperature in comp cell means. So remember that this comp cell works by flipping spins of pixels, right? And this spin flips, they are always accepted when that is lowering the energy of the simulation, okay? So when you flip a spin to the neighboring spin pixel, you accept the spin flip with probability that's equal to 1 if the difference in your energy is negative. So if you decrease the energy of your configuration, or in other words, you're satisfying all the constraints that you put in your cost function or your Hamiltonian, then you always accept the spin flip, okay? But if you do a simulation that is only like that, everything would froze very easily to a global minimum of configuration, and nothing, and your system will not evolve to a global minimum of configuration. So what you do, you also accept your spin flip, even though your energy is momentarily increased by your spin flip. And the criteria for this, so if your changing energy is actually bigger than 0, you accept the spin flip with a exponential probability to the minus the changing energy divided by what's called the temperature of a simulation. What this means that the higher this T, the more likely you are to accept all spin flips. If your T is 0, then this probability is going to be 0. Then you have e to the minus infinity and 0. So your acceptance is, probability is, and this the changing energy would be 1 if the changing energy is 0, so this is 0, and it decays an exponent if you're changing energies higher than 0. So for spin flips that only increase the energy a little bit, you always accept it. If you increase a lot, it goes way away than what the cells are supposed to do, then you accept a very low probability. And when you change your temperature, this parameter here, what you're doing is you either make this more restrictive or more acceptive. So this is going to be a low temperature. You only accept flips that are negative or very close to negative. Or if you have a high temperature, then you start flat out towards the 1, and then you can accept any spin flip. If you make a hugely high temperature, then you are basically accepting all spin flips, even though it's not obeying your guidelines in your constraints. The volume constraint is increase the volume from 1 to 1,000. It's okay, you accept in this case. But if you increase the volume from 10 to 11, it doesn't see a difference. So, and if you make a temperature of almost 0 or even T equals 0, then you basically have just, so this is going to be T equals 0. Then you only accept spin flips that are diminishing temperature. But this is also bad, because imagine a cell that the only constraint is its volume constraint. As soon as its volume reaches the target volume, you don't accept any other spin flips. So the cell will be effectively frozen at that state. Because any other flip, either you are losing, moving away from the target volume, or by diminish the cell, or you're moving away from target volume by increase the cell a little bit, and then you never accept these spin flips, and then your cell never evolves. So you have to allow some kind of movement. You have to accept some spin flips that increase your energy temporarily, and then eventually you are driving back your energy too. So you want to let your system fluctuate around the ideal value, so your system can actually evolve. So here in the simulation, what I did, I increased the temperature to 20 to make the cells jiggle a bit more. So the higher the temperature are, so this parameter called the temperature can be interpreted as the summability, intrinsic summability, because the higher it is, the more the cells change their shape, so they are more active in a certain way. Make sense? Well, don't think of this as temperature. Think of this as the intrinsic noise in your stochastic simulation. Yes. You have to allow some noise for things to move around, right? So if you have a jar full of balls, and you just put the balls here, they are on the top, but if you shake a little bit, they'll kind of, that shaking, that noise that you add to the system, the temperature that you add to the system, allows the things to settle, and then it goes down. It sets the scales of the energy. If you multiply this by 10 and everything else by 10, all your lambdas by 10, you have the exact same result. Yes. Yes. Okay. So here what you see is that I increase the temperature so the cells go jiggle a bit more. And when I have a target volume that's very low, I'm actually collapsing all the green cells, and I'm actually driving some kind of cell sorting in the system, right? We can also do the inverse. We can increase this target length to, instead of 4, 2, we can make it 14. Right now, what do you guys think will happen? Okay, let's see. So what's happening now is that now the cells, they have a diameter of 7, and the links have a target length of 14, which is 2 times 7. So the ideal configuration for your cells to be like this. 2 cells diameters away from the connected neighbor. Of course, here the cells cannot really go up because they are meshed out. But one thing that you can do, you can change this maximum distance instead of 20 to, let's say, 15. Oops. And this will make the links more prone to breaking, and you can have more remodeling of your system. Yes. You can also do that, yes. Let's try to do this. I don't know if it's going to work. But it's not really working, at least from this interactive mode. But you can redo a simulation. Let's diminish this to, instead of having 6, let's make this 3. That makes this 14, and make this 15. So it'd be very easy to break the links for small fluctuations. And then let me here also increase the temperature to 20. And let me just run the simulation again. Okay, let me just stop and do the simulation again. So you're concerned because you see this, a cell has a link with other cell, but not really touch the cell, right? Well, initially they are touching, then so they form the link, but eventually they move but because the target length is not the cell diameter, but 2 times that, they move away. Okay, that's not very realistic if you talk about cells, right? But it's something that you can do. I'm showing this to show how as Maciek did earlier this morning, just to show how the algorithm works, right? So here you're in a situation where ideally all the green cells will be about a cell length away from the next green cell. So this is another way to induce a checkerboard pattern in your simulation. Okay, in this region where you have a little bit less density of green cells, that happens better. Here, not quite so well, but you can also change the ratio of cell A to cell B, and then you can get a better output. So, no, what I did here is that, so Jamie, we just, all the links except between the cells green and green. And then which make the target length to be, instead of being 7, the diameter of the cell, to be 14, 2 times the diameter of the cell. That's why they form a link and then they'll try to push each other away, creating a checkerboard pattern. So